So happy Monday. Welcome. We are here. We've been on the main topic of weather theory. A lot of weather theory eventually moves into weather products. Um, I usually like to start with a good, general good morning. Is there any opening statements or comments from anybody in the group? Questions, comments, concerns, funny jokes, anything good that, anybody wants to share with the group?
I'm pretty much going feral over here.
He's going wild. All right. There's a good comment. It's a good comment. Appreciate that.
The weather lately has been a good example for the high, low pressure, all those examples. What else? Just mostly stuff we're going over right now. And if you've been paying attention, been outside, you'll notice certain clouds and you'll kind of try to pay attention, guess, but not that good to really know what's what yet.
I love it. I love it. We're getting some participation. We are on the topic of weather, and the weather is crazy today. What's happening out there?
Winds are changing constantly. Clouds are kind of moving at times. It all depends where you're at, but just trying to say what I see.
I love it. We really appreciate the participation. This is a great time, the beginning of class. Everyone's getting their brains warmed up and woken up. And Nick is noticing that the weather's changing out there. It's a great time for open floor. If there's any other thoughts, questions, comments.
Did anyone else notice the snow the other night? It was like a odd mixture. Like it was kind of raining and then it turned into like a snow kind of mix.
Yeah, I saw that too.
Yeah, it was weird.
A bunch of hail down in like Lafayette area.
Hail is very serious. Gosh, man, imagine flying your airplane, 100 miles an hour and then ice hitting your aircraft. Bad news. It'll take down airplanes. Jet engines do not do very well when ice balls start flowing into the intake ports. Windscreens, windshields crack. I mean, all sorts of bad drama. Hail is some serious stuff.
The first time I went to a Discovery flight, the airplane actually had a hail damage and decided not to do it.
Decision making. No-go decision.
Yeah, I started close.
Some talk about the clouds.
Okay.
Cool. Well, weather is a huge topic, and we're going to continue diving into that topic of weather. If we want to, we could actually start our day by glancing at some of the current weather products and looking at what the current weather is going on, analyze the real world application of it. Before we get that deep, I would like to say thank you, Chance, for making it in there. I see you there. I'll change you in the grade book here. The idea is a few administrative things before we get going. I've been sending emails back and forth, communication for emails with everybody. And there's some of y'all that I'm not getting good positive communication with. So right now, while I have you in front of me, it'd be people like Cameron Swank, Chance, Charles, Christian, Isaac Nesbitt, Jacob Wheat. So if you're one of those people, Jacob Wheat, Isaac Nesbitt, Christian Navarro, Charles Cassale, Chance Maringer, Cameron Swank, if you're one of those people, we need to have some good communication with the email. You need to check your email and respond. One of the assignments I'm giving is literally just points for you to respond back to an email. So if you're not seeing it in your inbox, You might need to check your junk folder, your spam folder. I'm able to see your email address in Blackboard. I believe everybody has the correct email address in Blackboard. So check your emails and make sure to respond back for some easy points. So that was one of the things I wanted to be sure to bring up with everybody. The next thing I was supposed to bring up, administrative, is I've received extra information about this pass, no pass, the pass fail that Nick was asking about last time. So on the Blackboard, I've published a new announcement. There's a new section. It's a piece of content. It's a PDF file of frequently asked questions surrounding the whole pass, no pass issue. And basically, the university is just giving extra grading options now that we're now remote people, distance education. Me as the instructor, I do the exact same thing. I give you a letter grade, A, B, C, D, F. If you, the student, would rather set up to be pass, no pass, or if you, the student, rather see your grade be pass or fail, you would file paperwork. So you as a student would file paperwork that says you would rather have a pass-fail type of grade instead of traditional letters A, B, C, D, F. If it's a C or better, you'd be called pass. If it's a D or F, you'd be called a fail. Me as the instructor, I don't do anything different. I just assign you the same letter grades. So the only difference would be GPA. If you are a person that really worries about your GPA, if you're a person that has a 4.0 and you think that this distance education format's really going to screw you up, you might possibly want to do a pass-fail if you thought that your grade was going to be a C. Because if you thought your grade was going to be C and that would hurt your GPA, you would still get the pass, you would still get the credit, but it wouldn't necessarily bring down your GPA. Looks like Isaac's getting in. That's a positive. All right. And then if you was going to get an A or a B, if you were on track to get an A or B in the class anyway, then you might want to go ahead and keep your normal letter grade. I believe you have until May to make your decision. And there's a new PDF document on Blackboard that's all about the frequently asked questions for the pass-fail. So I just wanted to be sure administrative to bring that up to everybody to let you know that exists as well. Okay, so everybody's talking about it, the weather. One of the biggest conversations is always the weather. So let me see if I can share the screen. So at this point, I believe that everybody should be seeing the weather chart. Is that correct?
Yes.
Yeah, it's correct.
Cool, awesome, thank you. So here is what's called a prog chart. I would actually call this surface analysis chart. Surface analysis chart. How did I get here? One of our favorite websites is aviationweather.gov. Aviationweather.gov. When you go to aviationweather.gov, you have a few of these options at the top. Home, advisories, forecasts, observations, tools. You click forecasts, there's a drop-down menu. Prog charts. So I'm going to go ahead and click prog charts just to show you. Prog charts. Then you have the options to study weather, all sorts of different prognostic. Prognostic is a fancy word for analysis. A lot of different analysis charts. And they're all great weather products. This is the one I'm going to focus on today. It says surface plot. The very first prog chart that loads up is the current. So when you click prog charts and you click surface plot, the very first that loads up is called surface analysis. And you can see that at the top left, surface analysis. Then you have the options of looking at this current chart, studying this current chart, or you could start analyzing and studying forecasted future analysis charts. You can do that with the drop-down menu to choose what specific time frame you want to study. You can do it with the arrows left and right. You go right to go 6 hours into the future. You can hit thumbnails to get a small thumbnail pictures of all the forecasted charts. So this is a really, really good tool that we can use when we're trying to flight plan and study what's going on with the atmosphere outside. So right now, what's going on with the atmosphere outside? Well, first things first, let's have some review. We talked about high pressure. We talked about low pressure during our last session. Right now, I'm looking for some participation. Who wants it? Do you think we're dominated by high pressure or low pressure right now?
Low pressure.
High pressure.
The answer is low. I heard more answers of low pressure. Good job, team low pressure. Whoever was saying high pressure, we're just a little off there. So if you analyze it, over top of the Michigan, there's a big red L. We can see that. Here over the Great Lakes area, there's another big red L. So the big red L signifies an area of low pressure, L-O-W, low pressure. Remember, the L's of a low pressure system, it's left-hand turning, it's lousy weather, it's lifting force, it's less stable. So when I draw with my mouse, when you're drawing on my mouse with the screen on the weather chart, you're seeing a counterclockwise rotation. That's a counterclockwise rotation of what the winds are trying to do. They're trying to follow the isobars. So these small gray lines are isobars. They connect areas of equal pressure. This is review from last time. Currently, we have a big blue line that stems in this area. That big blue line with blue icicles is called a cold front. Not only do we have a cold front, we have two cold front. Here's the second cold front right in front. That's more of on the eastern side of Ohio. Here's another cold front that's more on the western side of Ohio. So that is exactly what this chapter is all about, weather theory. One of the big vocabulary words is front, F-R-O-N-T. If you're taking notes, a front is a boundary layer between two air masses. A front is a boundary layer between two air masses. So what's going on is that we have a boundary layer. It's a division line. It's a zone of change. And that zone of change is bringing some really strong winds today. We discussed these isobars, these lines of equal pressure. When the isobars are very close and tight together, that shows a very strong pressure gradient force. That's one of your other vocabulary words, pressure gradient force. So let's compare some examples. Following my mouse is at the very top northwest portion of the screen, almost top center, very left. There's a big H, a big high pressure system that's over Canada. Remember, high pressure, it lives in the upper atmosphere. It pushes air down in a clockwise rotation. That high pressure system is more stable air, better flying weather. That high pressure system pushes down clockwise. If you notice in this high pressure system, the isobars are very far spaced apart. The isobars are very far apart near the high pressure center. You can actually see the high pressure center is labeled in millibars, M-I-L-L-I-B-A-R-S, millibars. That is a unit of measurement for pressure. So here's a high pressure center, 1032. 1032. I can't quite see what this high pressure center is because it's just off the chart. But we can see the gray isobar has a pressure of 1024. We need to know the standard pressure, 1013.2, 1013.2. And so each line that exists between the high pressure center and the low pressure center, each one of these gray isobar lines is showing another step down, another area of changing pressure. So here's 1024. As you get closer to the low pressure center, 1020. So that was an increment of 4 millibars in this example. So the next would probably be 1016, 1012, 1008, 1004, 1000 even. You know, and eventually it steps down so much that we're seeing low pressure centers of 990, or this one's even deeper, 987. So standard pressure in millibars is 1013.2, 1013.2. But that's just standard. When they decide to call it a high, when they decide to call it a low, when the weatherman decides what to label it on the chart, it's based off of relative pressure. One air mass is relatively higher pressure. The next air mass is relatively lower pressure. Some of the big things on this chart was the cold front. We have a cold front that just moved through. It's bringing a lot of change outside your window. With that cold front, it gets its name. The front is named describing the air mass behind the frontal zone. So remember, low pressure system rotates counterclockwise. So as this air mass rotates counterclockwise, it's bringing the colder Canadian air down and around. And here is the cold front, the boundary layer that's separating the slightly warmer air ahead of the front versus the colder, more dense air behind the front. And in the actual frontal zone, there'll be a lot of lifting force. So that is cold front. Let's have some participation. Who wants it? Right stemming out the northeast side of this low pressure system, there's a red line with half suns. What's this weather phenomenon going to be called?
It's going to be a warm front.
Tell me about a warm front.
It's a little rougher. That's a boundary layer of warm moving air, essentially, and it appears that it's moving kind of northwestward, I would say.
It wants to move north. It wants to move northwest. But the problem, so you are correct. Great answers. I really appreciate the participation. So we have a new weather phenomenon called warm front. It is an area where there's warmer, less dense air that is trying to spin counterclockwise rotation. But the problem is that the warm front is not as strong. The warm front is slower moving. The warm front, yes, there is lifting force, but it is more stable lifting force. It's not very rapid of a lift. It's a more stable lifting force. And why does that warm front move so much slower? Why does that warm front not have as much power? Well, warm air is less dense. Cold air is more dense. So these are some basics that we're trying to understand for weather theory. Warm air is less dense. Cold air is more dense. So with the warm front, you have an air mass of warmer temperature that's trying to push against an air mass of colder temperature. So in this example, we have a warm front that wants to rotate counterclockwise around the low pressure center. But as the warm front starts moving north, it's going to encounter the extra cold air that's in Canada. That extra cold, dense air provides extra resistance, and the warm front does not move very fast. Okay, so let's focus on this low pressure center underneath my mouse in the Great Lakes area. The cold front is almost on top of the warm front. Well, how about some participation? Who thinks what might happen next as this cold front gets really close to this warm front?
It's going to get occluded.
Good. So I heard somebody say the correct answer, occluded. Occluded. O-C-C-U-L-U-D-D-E-D, occluded. Occluded front. So occluded front is where the cold front catches up to the warm front. So in an occluded front, we have twice the amount of lifting force. Why? Because there's two fronts. So with a typical front, with one typical front, you have two air masses, the air mass ahead of the front and the air mass behind the front, and you have one lifting zone which happens in the frontal boundary area. That is a typical front, whether it's cold front or warm front. We know cold front is more lifting force than the warm front. Throughout the life cycle of the low pressure system, this is a fancy vocabulary word called cyclogenesis. C-Y-C-L-O-G-E-N-S-I-S. It's a fancy vocabulary word called cyclogenesis, the life cycle of a typical low pressure system. As that cold front wraps around the low pressure center and catches up to the warm front, the cold front can actually overtake the warm front. When this happens, the fronts zipper shut, and now it's called occluded front. And so in this picture, that is what I would predict is going to happen next in the future. In an occluded front, there are now two fronts interacting on each other. In an occluded front, there are now three air masses intermingling. So you can get some of the worst, most severe weather in some of those occluded areas. It is a sign of serious instability in the atmosphere in that area. Occluded front is going to be characterized, depicted by purple. So they'll have a purple line and we'll have intermixed half suns and intermixed icicles. So half circles and triangles. And it will be purple in color. So if I had to predict the future, that's what I think is going to happen in this area. A few more basics about weather charts. Over here, if you follow my mouse, California, Nevada, Utah area, I have a front, a boundary layer between two air masses. I'm looking for some participation. It has red half suns on one side and blue icicles on the other. What's this front all about?
Stationary front.
What do we need to know? Why do we care? What's its characteristics?
It has no relative movement, really.
We will say the words little to no movement. Yep, that's good. Good answer. Little to no movement. So it is a front, yes. It is a boundary layer between two air masses, yes. But one air mass cannot overtake the other mass very easily. So they're almost like a standstill, like a game of, chess. I don't know if that's a good example. Like a strategy game where neither party can move forward or advance. So stationary front, yes, it's a lifting force. Yes, it can cause weather. Yes, it's a boundary layer between two air masses, but neither air mass has that much steam, that much energy to try to overtake the other. Okay, so we're reviewing our weather charts. There's some very fancy symbology on this chart that we're getting to, but let's make sure to cover the basics first. Here's another chance for some participation. We have a orange, yellow, tan line. In fact, let's use a better one. Here we go. Off this low pressure center in Michigan, there's a long dashed orange tan line. I'm looking for some participation. What is this?
Trough.
That's a trough.
Yep, I agree.
Yep, with a T, trough, T-R-O-U-G-H, trough. And what do we know about trough? Why do we care?
It's an elongated area of low pressure.
What's that mean to us as a pilot?
Means it's probably
bad weather.
Yep.
Lifting
simple bad
force.
weather.
Yep, it's an area of lifting force. So a trough is very similar to the idea of a front. In fact, a front could lose energy and become a trough later in its life, or vice versa. A trough could gain energy and become a front later in its life. So this trough is a line, an elongated area of low pressure. We know low pressure is a lifting force. Is it a boundary layer? Yeah, it's a boundary layer between two air masses. We have the air mass that's ahead of the frontal zone and the air mass behind the frontal zone. However, it's not a front. Why? Because the characteristics of the air mass ahead and behind are not that different. There are only three elements of an air mass, three characteristics of an air mass: temperature, pressure, and moisture. So with that trough, the air ahead of, the air behind that trough have very similar characteristics of temperature, pressure, and moisture. But there is a boundary line developing. That's why they labeled a trough. There is a lifting force there, but it is not yet a strong front. Trough. Okay, so we've covered the basics of this chart. There's a new symbol on this chart. Ooh, congratulations, hooray for new. Who can help us out? It's a red line with double dots. Wow, what's up here? Maybe
I'm
nobody knows.
guessing some kind of cold front mix that's like cold and low pressure.
I'm gonna help you out, and I'm gonna give you a new vocabulary word. I appreciate the participation. The new vocabulary word is squall line. S-Q-U-A-L-L, line. Squall line. So this is the depiction of a squall line. When we say squall line, we are talking very serious weather. You do not want to fly your airplane near that weather phenomenon. Squall line. So by definition, what is squall line? It is a very narrow band of very active thunderstorms. So along this whole line, if you pay attention to the radar today and you study radar charts and you look at convective activity charts and thunderstorm prediction centers, you're going to see a lot of thunderstorms developing in this area where that squall line is depicted on today's surface analysis chart. Squall line, very active, narrow band of thunderstorms. Squall line, it's super dangerous because you as a pilot may not be able to find a hole to get through that line. So you imagine if there was a pilot trying to fly from east to west or west to east in that area, there's a line of thunderstorms. You know, sometimes there's a cell of thunderstorms and you might go around it. Really, we don't want to fly near thunderstorms at all. But if you spend enough time flying airplanes, you'll probably find yourself flying airplanes and there's bad weather in some cases. Again, never go flying on a bad day if you can help it. Make a no-go decision. That's usually the best answer. Heaven forbid, if you're ever flying an airplane and there's a thunderstorm out there, it doesn't mean it's the end of the day. You might be able to still navigate around it. There are a lot of airplanes that navigate around thunderstorms. The FAA says we should stay 20 miles. That's one of your test questions. We're supposed to stay a minimum of 20 miles away from thunderstorms. 20. FAA recommends 20 miles that we stay away from thunderstorms when we're flying. Most pilots have a personal minimum that's more of 40 miles, 40 miles away from thunderstorms. The problem with squall line is that it's a very narrow active band. So as that band of thunderstorms that's ranging from north to south, any airplane that wants to travel east to west in that area is probably not going to be able to get through because they're looking for a hole that they can fly through. And that's bad because this whole line is convective activity. There's lifting force, there's moisture, there's unstable air. All the ingredients are there for very serious weather, very serious thunderstorms. The other day, people talked about hail. I mean, that's exactly what's going to be happening in that area. So this new vocabulary word, this new symbology on the chart is called squall line. In this picture, it is a red line with double dots. Huge vocabulary word, and it's so dangerous because you may not be, as a pilot, you might not be able to pass through that area because the line is so long of thunderstorms. Many squall lines that I see actually range from Canada to Mexico. They're so long, they go hundreds of miles long. You're going to have test questions about the squall line. So here's some more test questions on the squall line. You'll have a test question about squall line, and it will ask if it is a frontal, if it's a frontal phenomenon. Is a squall line associated with a cold front? The correct answer on the test is no. The correct answer on the test is that no, a squall line is non-frontal. So by definition, the FAA says that a squall line is non-frontal. I disagree with that slightly, but I'm going to try to explain it to you. The reason why the FAA says that on the test is that the weather, the thunderstorms, the squall line does not form in the frontal zone. So if you're following my mouse on the screen, the cold front is the blue line with the half icicles. That is the cold front. That is where the lifting force exists for the cold front. You can have some cold fronts that are so strong that they disturb the air mass several hundred miles ahead of the frontal zone. So people talk about outflow boundaries and gust fronts. That's what we're talking about. We're saying that this cold front is so strong, moving from the west to the east, that it is pushing air several hundred miles ahead of the frontal zone. And that air is getting pushed so far ahead that thunderstorms are developing ahead of the cold front. So by definition, a squall line is non-frontal. The actual thunderstorms of squall line are not developing in the frontal zone. They are developing ahead of the cold front. How far ahead of the cold front? 50 to 200, 50 to 200, 50 to 200 miles ahead of the cold front. That is where the squall lines can develop. So in this case, you're seeing the squall line here of, say, eastern Virginia versus the actual cold front, which is maybe more of western Virginia or eastern Tennessee. So that was a lot of information. And it was all brought on by you guys wanting to talk about the weather. Hooray! Weather theory. And this is today's weather surface analysis chart. What kind of thoughts, questions, feedbacks do we have about any of the information we've been going over so far? Okay, so what I would say is good information also. Any chart that you study, any weather product that you study will have a legend. And it is very wise for you to study the legend. Unfortunately, we will not cover every single weather product that the FAA creates, that the National Weather Service creates. We simply cannot study every single product. And you all are taking a written exam. I didn't write the written exam. It's written by the FAA. And unfortunately, they're going to test you and quiz you on a lot of different weather products. Some of those weather products are old and not even in service anymore. So it's a very strange thing that the FAA does to the pilots. They make the pilots, you, study all these different weather charts, and then some of these weather charts that you spend time studying are not even in use today. You get on aviationweather.gov, the website, and you don't even see some of these weather products in existence anymore that you still had to study to learn to be able to take the test. So the idea is that, you know, us as a class, we're just not going to be able to cover every single weather product that exists. There are people that spend their whole entire life studying weather. They get, you know, all sorts of degrees in weather. It's a huge topic. I'm doing the best I can to enlighten you and hit the high points. This is going to be some of the high points, a lot of the things that we've talked about today. And as I'm trying to give you tips, I'm giving you tips of how you can, you know, pass that written exam easier. One of the things to be aware of is the legend. So every chart that you find yourself looking at has a legend somewhere nearby. If you're taking the real FAA written exam, you'll find it on that piece of paper, somewhere scroll down on that piece of paper. So for today's example, I'm looking at my screen where I have today's surface analysis chart. I'm going to scroll down, and when I scroll down, I start to see some of the actual symbology, the legends explained. Here's where it's showing us the different occluded front, cold front, warm front, stationary, trough. It's showing us the different pressure systems, high, low. And then here, they're showing you a depiction of what the different colors could mean about precipitation, rain, snow, mixed, ice, thunderstorm. What you're finding is that we don't see any of this precipitation forecasted on this particular chart. Why? Great question. I'm glad you asked. Why? It's because this chart is the surface analysis chart. It's almost a current historical chart of what has been documented. It's not until we go into the future, if I click this button to go right one time frame into the future and look at a forecast, now I'm looking at the forecast, and this forecast will now show the prediction of precipitation. And that's where we start to see all the colors like before. And here on this forecast, we see some of the things that we predicted might happen. Notice the purple, the occluded front we talked about. Okay, so this has been a lot
Yeah, I
of
see it.
awesome. Thank you. Thank you for the feedback. So weather is an exciting topic. We love it. We got to respect it, and we try to understand it to a new level. Great. So at this point, I feel like we've done a great job of getting everybody's brain warmed up with weather. We still have a few more minutes before we think about taking a break, so we need to try to continue covering material with our presentations. So at this point, I'm trying to load up. And this is where we left off if I hit the screen share button now. Okay, does everybody see the PowerPoint?
Yes.
Yep.
Yeah.
Awesome,
Yes.
cool. So this is the picture that we left off on last time, which was where we're showing examples of these pressure systems, high, low, clockwise, counterclockwise rotation. This is where we left off, and we even furthermore dove into a real world example today, analyzing more of that. I click forward next. The next topic at hand is called Coriolis force. I'm going to start by just reading it to you. It's an apparent force that causes a deflection in the path of a vessel moving in a straight line when observed from the Earth. Okay, the deflection, Coriolis effect, is due to the Earth's rotation and is to the east when the motion is towards the pole. Goodness. Okay, so what's going on with Coriolis force? The idea of Coriolis force is that planet Earth is spinning on its axis. I don't know if we have any flat Earth people here in the room or not, but science tells us that the Earth is round. Science tells us that the Earth spins on its axis. So the idea is that objects that are not attached to planet Earth, so let's say we have an airplane. Okay, cool. We like flying airplanes. If you fly your airplane straight north, if you after the fact analyzed your ground track actually will show a slight curvature to the right. So I'm going to say it one more time. If you flew your airplane perfectly north, your airplane is not attached to planet Earth. You fly north in the sky, you're not attached to the planet Earth, you're in the atmosphere, you fly straight north. If you analyzed your ground track, your path over the ground, it would actually slightly be deflected to the right. Your ground track would slightly be deflected to the right. Why? Because the earth is spinning beneath you and you're not attached to it. So then all of a sudden, Coriolis force is a phenomenon that we experience where objects that move through the atmosphere, even though they want to take a straight line, a straight path, they cannot. When we analyze their path and their track from landlubbers, from standing on the ground, we observe their path as actually having a turn, a deflection, say to the right. That's what Coriolis force is. For us flying a Cirrus SR-20 single engine general aviation airplane, this is not a force that we really see over the course of an hour, 2 hour, 3 hour flight. Even if we do go 150 miles an hour, it's just not a fast enough speed. It's not a long enough duration for us to physically see Coriolis force with our flight path. However, if you go on to fly the space shuttle, you want to go fly, Spaceship One, you want to go do some space, re-entering the orbit of the atmosphere. Wow, how cool would that be? Well, you are traveling so fast and you're covering so much ground that yes, it becomes a very serious conversation that you have to account for Coriolis force, how your path, even though you're traveling in a straight line, is not truly in a straight line as observed from the ground. So Coriolis force is going to really apply to weather, because our weather systems that we're studying, high pressures, low pressures, these air masses that are traveling throughout our country, they are going to experience Coriolis force. And this is one of the questions with your short answer homework. Why do the pressure systems rotate the way that they do, clockwise or counterclockwise? It's because of bing, 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 Coriolis force. So all energy wants to travel from high pressure center to low pressure center. All energy wants to travel from high to low. So in a perfect world, if the earth was not spinning beneath us, that high pressure would just move right on straight to the low pressure center, everything else being equal. But because there is Coriolis force, because the earth is spinning beneath us, that high pressure system, as the air moves towards the low, it gets deflected to the right, which creates that clockwise rotation for the high pressure center. This same phenomena can be observed on a merry-go-round. So say we all get on a merry-go-round and we sit across from each other on the merry-go-round. The merry-go-round goes really, really fast and we're spinning in a circle. If we took a baseball and we tried to roll the baseball straight across the merry-go-round, the baseball would not travel straight across the merry-go-round. It would get deflected to the right because the merry-go-round is spinning. So Coriolis force is a huge topic. I would really challenge you guys to, after this class, get on the YouTube and look up some videos on Coriolis force. There are some very, very educated folks that have made very good videos about Coriolis force, and it's a great topic that'll help you out. It's really fundamental for us to understand weather theory, and later on, if you want to re-enter a spaceship in the Earth's atmosphere, you'll talk about Coriolis force at that point as well. So this is us describing Coriolis force. Let's see if we can get through another slide or two. Frictional force. Okay, so what's happening with frictional force? Friction causes the wind to shift directions when near the Earth's surface. Frictional force reduces Coriolis force. That's really interesting. So as you learn to fly airplanes and learn how to study, analyze weather, one of the biggest conversations that I have with a lot of students, let's pretend it's time for you to take a stage check. You guys come to me, and unfortunately, I've had to fail many students on stage check for this big reason. The students don't always understand the difference between surface winds versus winds aloft. Interesting. So what we're explaining to you is that as a pilot, we're going to have to be able to analyze winds. And there's a lot of different winds that we might come in contact with. So if we're going to fly a long cross country, let's say New Orleans. I've been trying to get some student to fly me New Orleans for years. I'd love to go. It'd be great. Let's do it. So if we're going to go fly to New Orleans, we're probably going to go to a nice high altitude. I don't know. Let's say it's probably a little more westerly. So oddballs fly east. We'll go westerly, 8,500. Maybe we're going to go fly 8,500. Cool. I love it. We can study the winds for 8,500. That would be called winds aloft. And we would have an idea, headwind, tailwind, crosswind, what are the winds doing at altitude? Winds aloft. That is a different conversation than surface winds. So when you learn how to land or take off, and you learn how to pick what's the active runway, when you learn which way should I enter the traffic pattern, wind correction angles with surface winds for landing and taking off. So those are two different winds, surface wind versus winds aloft. So when I talk about winds aloft and I'm in the upper atmosphere, that's when we see Coriolis force really at play. Coriolis force is doing a lot of the influencing for the wind patterns. So this is some of your test questions on the written exam. I'm trying to help you out. The winds aloft are going to be very influenced by Coriolis force. In fact, I think the question, take notes on this, this is one of the questions on the written exam. It's that winds aloft follow the isobars due to Coriolis force. That's the question on the written exam, or that's the answer to the question. The answer to the question on the exam is that winds aloft will follow, run with the isobars. Winds aloft will follow the isobars due to Coriolis force. However, the winds at the surface will actually be deflected. They will not follow the isobars perfectly. They will be deflected due to frictional force. So we discussed this concept way back when we talked about aerodynamics. If you remember, we talked about drag, and we talked about skin friction drag, which was a type of parasite drag. That's exactly what's going on here. Only now, instead of describing it in terms of an airplane wing and how the air slows down and how the airflow changes near the boundary area of the wing, now we're talking about the whole atmosphere as an air mass. And the whole atmosphere has wind that's moving. And when you start to get near that boundary layer called the surface of the earth, where there's trees, lakes, mountains, cities, when you need that surface area, there's going to be drag that slows down the airflow. So frictional force is going to slow down the airflow near the surface, and we will have different winds at the surface, different winds aloft. Not only is it going to be different speeds, but it'll also be different directions. Interesting. So that's what this frictional force is showing us. It's showing us a low pressure center, and it's showing us the low pressure center, how it's going to spin counterclockwise and lift up air. That's going to be less stable. High pressure system is going to go clockwise and push down air. That's more stable. We define stability basically as lifting action. If there's a lot of lifting action, the air is less stable. Okay, so this has been us discussing Coriolis force and now frictional force. We're getting very close to finishing this slideshow. Looks like maybe we could do this one more slide and then we'll take our break. So here is our global wind patterns. And really, this is a review. I think we've already discussed on a lot of this. So earlier, we had a slide that was more three-dimensional, but this picture here is showing the same things we talked about. We talked about how we had something called a Hadley cell, a Ferrel cell, and a polar cell. And we've learned about convection. Convection is the transfer of heat energy through convective currents, through vertical currents in the atmosphere. So here you can see the lifting force that's happening around the equator. That's rising air, lifting force. That would be an area of low pressure, and that exists at the equator. And then our hemisphere is divided up into 30-degree increments. So then at the 30-degree latitude, we see an area of sinking air. That would be high pressure, where the air is being pushed down, and we have a circulation, a convective current in the air of how heat is distributed during that cell, in that cell. Same thing's going to happen up here at the 60-degree north latitude, and that's where we're going to see an area of rising air. That would be low pressure. And the review for us is that the jet stream develops. The jet stream develops at the 30-degree latitude and the 60-degree latitude. So we have two jet streams that can influence North America. We would have a subtropical jet stream, and we would have a polar jet stream. So those would be upper atmosphere phenomenon, and those upper atmosphere phenomenon would influence the weather that occurs at the lower atmospheres that we would fly in. You can see here that North America, we are what's called the westerlies. We are called the prevailing westerlies. So typically for us, we're going to see weather move from the west to the east. And that's why we said, if it comes from the east, it's a beast, those old weather sayings. So if you have a weather system that's moving from the east to the west, it's a beast. It's going to be a very strong weather system. Maybe one more of those old sayings, and then we'll take our break. The other old saying that you hear a lot is red sky at night, red sky in the morning. How does that saying go? Does anybody remember that one?
Red sky at night, sailors delight. Red sky in the morning, sailors take warning.
100% correct answer. So let's try to discuss this little weather saying, and then we'll take our break. So what do you think? Is it true? What does it mean? Does anybody have ideas? Why? Why would we have a red sky?
Maybe low pressure, high pressure differences and all the kinds of winds. And I'm just guessing, but
Pressure. It's all about pressure. So red sky at night, sailors delight. Red sky in the morning, sailors take warning. So we're sailors, we're flying our ships through the atmosphere, the sea called the air. And the idea is that we are very aware of high pressures and low pressures. So we know that the sun rises in the east and sets in the west. The sun rises in the east, the sun sets in the west. We know that the weather in North America typically travels from the west to the east. So what would make, we're talking about these motions, these times of the day called sunset and sunrise. That's when the sun is at the very lowest part of the sky, and we are going to see the atmosphere differently during moments of sunset and sunrise. Why? If it's 12 o'clock noon and you look straight up at the sun, you are seeing the sun directly through the lens of the atmosphere from above. But when the sun starts to get near like sunset or sunrise, we are actually looking through a bigger lens. The atmosphere is a bigger lens. There's actually more volume of air mass between the sun source and your eye. So 12 o'clock noon, the sun just pushing straight down on you. It's the least amount of atmosphere resistance for that energy to hit you. When you're talking about sunset or sunrise, because of the angle, you're actually looking through a very thick lens. The actual atmosphere itself is an extra thick, large amount of volume of air. And so what's going to create the most beautiful sunrises or the most beautiful sunsets is when there's extra refraction. So the idea is that if you have a lens that's extra thick with lots of crazy particles in it, with condensation nuclei, dirt, dust, pollution, all the different elements that are being trapped in that atmosphere, in that lens, that's what's going to create the most colorful sunset or sunrise. So in this case, we're talking about red. So a red sky at night, sailor's delight. So at night, the sun is setting to the west. So if you are looking to the west and you're getting a very red sunset, that means the high pressure system is to the west. So your current location, you look to the west, weather typically moves from the west to the east. If it's sunset and you see red sky to the west, then that means there is high pressure system to the west. And you expect that over the next day or so, that high pressure system will move from the west to the east, and you will have good flying high pressure systems on top of you in the future, in the next day or so. So that's red sky at night, sailor's delight. The high pressure system is to the west, coming your direction. We like high pressure system. High pressure system is up the atmosphere, it pushes down, it creates resistance. So any of that lifting force is meeting resistance, and so all the dirt, dust, pollution, particles are getting trapped in the atmosphere to create a thicker lens and extra refractions for all the light energy to create red skies. Red sky at night, sailor's delight. Red sky in the morning, sailors take warning. Well, in the morning, we would look to the east. The sun would rise in the east. So if we have a red sunrise, that means the high pressure system is to the east of us. Most weather is going to move from the west to the east. So if the high pressure system is already east of us, watch out, because that means there's probably a low pressure system that is west of us moving in. I know it's kind of confusing. I don't know if that helped or not.
Yes, it makes
It
sense.
kind
Yeah,
of
that worked. Thank you.
It did for
Cool.
me, yeah.
Well, I appreciate the participation. We're going to take a 10-minute break, use the bathroom, grab a bite of food, and we'll be back. Looks like we have Isaac after all. So Isaac Nesbitt made it. Awesome. Rodrigo made it after all. Cool. So I think we're back on. I think that it should be working. You guys hear me all right?
Yep.
Yeah.
Awesome. Good
sir.
deal. Good deal. See, I just want to mention it one more time. I have a few of you guys that I am not receiving good communication with on the email front. So that'd be like Cameron Swank, Chance Maringer, Charles Cassell, Christian Navarro, Isaac Nesbitt, Jacob Wheat. If you're one of those people that I mentioned, check your email. I'm giving you points as an assignment just to respond back to some emails. So maybe it went to your junk folder, maybe something weird has happened. But if we're not getting those emails, then we need to figure out what's wrong. If we need to change email addresses or what might be happening there.
I just responded to that email that you sent.
All right, so he's fessing up. He says, "I just did it." All right, so after this, I'll give you some points in the grade book when I find it in my inbox. Good job, Chance. Thank you.
You're welcome.
So today's topic, weather. Woo! Nobody's got any good weather jokes? So, we'll have to work on that. So we've been working on, everybody should see a PowerPoint at this point.
Yep.
Perfect. So we just covered global wind patterns. We're getting close to finishing this section. It says local wind patterns. There are several wind patterns near the surface of the earth that can affect local weather. Sea breeze, land breeze, valley breeze, mountain breeze, adiabatic winds. Pretty fancy vocabulary words. Okay, local wind patterns. I can dig that. So the first example is going to be a sea breeze. So you'll have multiple questions about this, both on the test for our class and the FAA written exam. So what I would try to help you out with is sea breeze. So sea breeze, we are saying that the wind is blowing from the sea to the land. So when you're trying to answer ABC, multiple guess, and you're trying to figure out about sea breeze means the wind is coming from the water to the land. When they say sea breeze, they're describing where the breeze is coming from. They're not describing where the breeze is blowing to, but where the breeze is coming from. Sea breeze. This is a convective current activity. So we've talked about convective currents, transferring of heat energy through the convective circulation patterns in the atmosphere. These are local patterns, more like a micro scale event. And here we can see on the slide with my mouse that the ocean is cooler compared to the landmass. It is a colder source, also known as a heat sink. It absorbs all that energy, and because there's convective patterns within the body of water, there's a lot of heat that can be stored and transferred inside that water mass. Versus where my mouse is now, the land mass. The land mass heats up very quickly and will give away its heat very quickly. So when the sun is shining throughout the day, we are seeing warm air rise over that land mass, which heats up more quickly. That rising air says that we could help form clouds. We would call that lifting force, thermals. Why does a cloud form? Oh gosh, that's a new topic. That'd be called condensation. So latent heat energy, there's only a few different forms of matter: solid, liquid, and gas. A cloud would be liquid. it's actually physical water droplet being suspended on a particle in the air, a particle of dust or pollution, debris, condensation nuclei. So the vocabulary word there will be called dew point. The air can only hold so much moisture. Air can only hold so much moisture. Warm air can hold more moisture than cold air. So warm air has a certain temperature, and then as the air gets cooled to the dew point, DEW-POINT, dew point, then the air can no longer hold all that moisture and will condensate out, spit out, squeeze out water droplets. And those water droplets will form on the dust particles in the air called condensation nuclei and create a cloud. So we are studying here the sea breeze, and we're understanding why the air could rise. As the air rises, it cools. As the air cools, it reaches the dew point, and then we transfer state of matter. Instead of being a water vapor suspended in the water vapor, it then condensates out, process called condensation, latent heat energy transfer, and becomes visible moisture. We call that a cloud. So goodness, we're seeing a lot of temperature change through this convective circulation pattern. And as this air moves out towards the sea, cooler air can sink and the process can start over again. So this process here is a convective current in the air, and we call it a sea breeze. For you to pass the questions on the test, you would really need to recognize that sea breeze is when the breeze comes from the water, from the sea to the land. The breeze that comes from the sea to the land, we call that a sea breeze. It is a type of local convective circulation pattern. Okay, if we check out the next picture, we have a land breeze. Same idea. We name this breeze based off of where the wind blows from. The wind blows from the land to the sea, the land breeze. Again, it is a convective current throughout the atmosphere in a local nature, in this local area of local coastal area that we're describing. And the ocean is warmer compared to the land. We've talked for lots of reasons why. So the ocean is translucent. Translucent means it has a clear, see-through property to it. So like when the sun shines on the ocean is translucent. So the short wave energy from the sun. The short wave energy from the sun is being absorbed at multiple depths because the ocean is translucent. So not only is it the surface of the ocean that's absorbing energy from the sun, but also 1 inch, 2 inch, 3 inch, 4 inch deep. You know, all these inches as you go lower and lower, deeper and deeper, they still see some amount of sunlight and absorb some sort of solar radiation. So one of the big things is that the ocean is translucent. Water is translucent, allows energy absorption at multiple depths. We've talked about how the ocean is a fluid. So because it's fluid nature, these convective currents that we were describing in the atmosphere also occur in the water, so that way the ocean can transfer its heat energy throughout the fluid. So the idea is that there's lots of reasons why the ocean is warmer compared to the land. And here we are showcasing what those implications might be. We have an ocean that is warmer than the land, so the warmer air is rising from that warmer water, and then we see the rising air, which is going to get cooled, because as we rise in the troposphere, we see the air cool generally at a rate of 2 degrees Celsius for every 1,000 feet. If you want to be a Fahrenheit person, there'll be certain questions on the written exam where you have to say in Fahrenheit. In Fahrenheit, we'll say 4.4 degrees Fahrenheit. There'll be questions on the exam where you have to do some math about what altitude will we see clouds form. And as the air rises, Fahrenheit style, we would do math of 4.4 degrees Fahrenheit for every 1,000 feet. In the pilot community, we typically talk Celsius, and so we see air cool, typically standard 2 degrees Celsius for every 1,000 feet. We all get it. The warm air rises over the warmer water, and it cools as it rises. That cool air can then make its way to sink over the land mass. Sinking air spreads along the surface. The land cools down more rapidly. Land cools down more rapidly than the water. The land will heat up more rapidly than the water. The water will retain its heat energy longer than the land. And so then we get to see this land breeze, as the breeze blows from the land to the water area. So this is a coastal phenomena that we would see happen with local weather patterns, sea breeze and land breeze. The biggest thing you can remember to help you out for the test is that the breeze is describing where the wind comes from. The sea breeze would be when we have the breeze come from the sea to the land. The land breeze is when we would see the breeze come from the land to the sea. Sea breeze, land breeze. All right, nobody's asking any questions. We'll keep moving on. Very similar ideas, valley breeze, mountain breeze. Exact same conversations, only now we're describing wind either flowing up the side of the mountain or down the side of the mountain. Huh, cool. So in this example, on the top, we have the fact that the wind is blowing from the valley to the mountaintop. So we're going to call that one the valley breeze. It's blowing from the valley to the mountaintop. So it's a circular pattern of air movement. We call that convection, and it's blowing from the valley to the mountaintop. That would be the valley breeze. It has a lot to do with unequal heating of the temperatures, unequal heating of the Earth's surface, unequal heating of the Earth's surface, unequal heating of the Earth's surface. That's the reason why all weather occurs. So the valley does not receive the same amount of solar radiation as the mountaintop does. So we have differences in temperature, which create differences in pressure. And the reason we have wind is because of differences in pressure. With this convective activity that happens, we then see the cooler air sink down in the middle of the valley, and then we see the valley breeze rise up the side of the mountain. Here in the bottom picture of the slide, we are seeing a mountain breeze. The wind is blowing from the mountaintop down to the valley. Mountain breeze, the air is blowing from the mountain to the valley. For the same reasons, unequal heating of the Earth's surface. For the same reasons, we have unequal pressure. For the same reasons, high pressure wants to go to low pressure. So in this case, we have a convective cycle that is being established where the air is blowing from the mountaintop to the valley. When it gets to the valley, we see a lifting force, and it keeps the cycle going. These pictures make me think about mountain flying. We're not in a mountain flying course today, but the idea is that, you know, when you become certified as a private pilot, you legally could fly your airplane to mountainous areas. There's a lot of different considerations involving the air flows and the wind patterns near the mountains. Some really just rough things to think about and put in the back of your brain. 2,000 feet AGL. So if you ever want to cross a mountain peak, if you want to ever go fly over top a mountain peak and you don't know what you're doing, this is your first time ever doing it, you should plan to be at least 2,000 feet above the ground level, above the highest peak. So whatever the highest peak is, you want to be at least 2,000 feet above that highest peak. Why? Because there's a lot of crazy wind patterns that can happen near the mountains. There's been a lot of airplanes that crash due to the crazy wind patterns near mountains. We need to respect the mountain winds, the valley breezes, and we need to be safe operating around those areas. So 2,000 feet above the peaks is a good guidance for trying to fly around mountainous area. Some other things to think about. If you are going to try to cross a peak, you want to avoid pointing your airplane directly at the peak, the ridge line. You want to avoid flying directly at the peak. Avoid flying directly at the ridge line. Why? Because some of these downdraft areas can then suddenly push you down into an area of rising terrain. So Mountain Flying 101 would tell you that if you are going to approach a peak, if you are going to approach a ridge line, you want to approach at a 45-degree angle. You want to approach at a 45-degree angle. So let's say the mountain was straight west. You're pointing straight west and you're pointed directly at the mountain. It would be less safe. It would be more foolish to fly directly at that peak going straight west. You would rather approach at a 45-degree angle, say heading 225 southwest. Or you could go northwest, maybe heading 315. You would like to approach at roughly a 45-degree angle or so, and that way you're already halfway through a turn if you needed to turn around. So we are learning that valley breezes and mountain breezes exist. There's some very strong local wind patterns that can happen near the mountain ranges. For the day of the test, you need to learn some very basics about valley breeze, means the wind is blowing from the valley to the mountaintop. Mountain breeze, the wind is blowing from the mountaintop down to the valley. And we also learned over some basic rules of thumb for mountain flying, which could be several hours worth of conversations on its own. Okay, we'll keep moving. Adiabatic winds. We have an area of high pressure, we have an area of low pressure, and we have something called pressure gradient force. That's where the isobars are really closely spaced together, and there's a very large pressure change over a very small area. So pressure gradient force is causing the air mass to move from high to low. In this example with adiabatic winds, it's a very similar idea in the fact that there's a high plateau, an area of higher elevation, mountaintop, if you will, and then there's a downslope, and the air that's rushing down that slope becomes very, very strong, very, very serious. If you was an airplane in the wrong place at the wrong time, that air mass rushing down the slope could literally push your airplane into terrain. So this is a very famous vocabulary word. Adiabatic winds exists near mountainous areas and can literally downdraft, push an airplane into the terrain. So if you're not familiar with some of the local mountain flying for those particular areas, try to use some of those rules of thumb. Stay at least 2,000 feet above any peaks. If you are going to have to fly towards a peak, try to approach it at a 45-degree angle. If it's a really strong wind day to begin with, make a no-go decision and go try it again on another day when it's more calm. I've been lucky to fly from Indiana to California 3 different times now. Every time that I do it, I take the southern route. I go several hundred miles out of my way to go south around like Santa Fe, New Mexico, because in a small general aviation airplane, you're not going to have a lot of options if you get caught in some serious winds trying to cross over the tops of the Rockies around Colorado. So I usually go several hundred miles south out of my way for more of a southern route. And years ago, when they were developing that area, that's where they built that famous Route 66. So you're really just going to kind of follow some of those famous landmarks would be my better strategy. Avoid the adiabatic winds. So that's the end of this show. That was the basic weather theory, if you will. Let's see, let me click stop share. Okay. I'm clicking buttons on my end to get our next section going. So at this point, so are you guys seeing, it says weather patterns? Is that what you're seeing right now?
Not yet. It's still a black screen for us.
Yeah, I got low.
There you go.
Gosh, sometimes you got to sip some coffee. Anybody got any good weather jokes yet?
They're not hot right now.
Something about hot?
I said
The overall that way mass. If we are in the desert, it is a dry air mass. So we see very drastic temperature changes between 12 noon and midnight. And that leaves the ambient environment, those air molecules that was surrounding the water molecule, skipping ambient environment. The next would be sugar.
Well, if you want to shut the program altogether, if you hit Alt F4, it'll cut it out. But I don't know about the keyboard.
Yeah, unfortunately, I think that'd screw us up though, because we need to save this video after it's done.
Hovering over Alt Q.
Alt Q. So in a few moments, I'm going to hit Alt Q, and I think that will end the meeting. And I hope that our recording gets saved as it should. But I don't want to leave y'all if there's any other questions.
Thank you.